of years ago in the class, we had a bet. We were talking about a situation in which there was a rigid body floating around in space, no gravity, perfectly rigid, but somehow you have an ability, let's say you have two jets where you are applying equal and opposite force at these two locations. So you are really generating a pure couple. So the bet in class was, when you are able to do this, then what do you expect the motion of this rigid body to be? Will it be pure rotation? Will it be rotation plus translation? And if it is rotation of any form, will it be rotating about a point which is at the center of these two forces, or will it be rotating about some other point? This is something that you can actually try at home. You might be wondering, how are you going to set up an experiment where there is no gravity, where something is floating around in space? But in the class, students were able to figure out a simplification of this where you could do this experiment at home. So we'll come back to this. So today we'll really be talking about kinetics. So this is, again, to remind everybody, this is a refresher concept capsule series. And again, just a disclaimer, please remember these are all quick and dirty proofs. These are not necessarily fully rigorous proofs. So you really have to do these proofs yourself for you to fully gain confidence on these concepts. The discussion here will only serve to give you an overview and a quick idea about some of these concepts. The other aspect that I always tell all students is that the concepts are relatively simple, but you really have to apply them. You really need practice applying them in various different situations. You need to develop experience for you to really gain mastery over these concepts. So remember these things while you're going through this. So let us go back to our basic Newton's second law, F equals ma. Now let's see what happens to this once we take moments. So for that, let us go back to our systems of particles. And in our systems of particles, if you remember, we had thought of two particles I and j. Of course, there are n of those, but our focus is on the ith particle. And we would say all the external forces acting on the ith particle, their resultant together is called capital Fi. And the internal forces acting on the particles due to each other, they are called Fij and Fji. So Fij is the force acting on the ith particle due to the jth particle, and that is equal and opposite to Fji. This we had already discussed. Now, if we write the Newton's law for the ith particle, we get Fi plus summation over j Fij is equal to MIAI. This we have seen before. Now let us take moments on both sides. So let us do Ri cross both sides and sum over all I particles. So when we take moments on both sides and sum over I particles, the left hand side of this ends up being Ri cross with Fi plus sum over j Fij, and the whole thing is sum over I particles. And it is easy to see that the first term here is really the total moment of all external forces. And let me now switch the subscript. I would say about point O, because if you recollect, all our position vectors were originating from point O. The second part of this equation, that actually sums to 0. Now, we already talked about the fact that if we do a double summation Ij, Fij, the fact that you have equal and opposite forces makes that summation go to 0. But in this case, we also have a moment here, and that moment Ri is changing with I. So how is that still 0? So Fij and Fji are equal and opposite. Even if I have two different vectors with which I'm taking moment, the fact that they have the same moment arm and they have equal and opposite magnitude makes it such that Ri cross Fij is equal and opposite to Rj cross Fji. Therefore, this second term goes to 0. So left hand side is simply the sum of moments of external forces about O. The right hand side of that same equation ends up being sum over I particles Ri cross with MAI. And here again we will use the decomposition that we spoke about last time. So that is Ri we can write as a vector sum of Rg and Rij. That is position vector of ith particle you can write as position vector of center of gravity plus position vector relative to the center of gravity. So we do that and we would get this is Rg plus Rij cross with MAI. And this I write as Rg cross MIAI. By the way, I forgot to put an I here. These should all be MI plus sum over I Rij cross with MIAI. And it should be obvious that this is, I can take the I summation to the second term here, and that is nothing but total mass of the system of particles, so m times acceleration of center of gravity. We go to the second term we can write as a sum of two further terms, where I write now Mi, this Ai I further write as Ag plus Ai with respect to G. And here you can see that the first combination ends up being 0 because sum over I, Rij, Mi I can always bring here in that summation, that ends up being 0, and this gives me the first term is Rg Mag. The second term boils down to just sum over I Ri with respect to G cross with MIAI with respect to G. Now let us take a look at the second term in more detail. As you may recollect, the equation for a general acceleration has a number of terms as we had derived in the kinematics concept capsule lecture. But here let us make one more assumption, that let us suppose we are looking at a rigid body, and if we are looking at a rigid body, then we know that the distance between the center of gravity and the ith particle is not changing. That simplifies the equation that we are dealing with, and we can therefore write the acceleration I with respect to G as simply alpha cross Ri with respect to G plus omega cross Ri with respect to G. We don't have to worry about the other terms and the Coriolis term and so on and so forth. We are left with only these two terms. Okay, when we examine these terms carefully and we put them back in that equation, if I look at only the second term there, that was sum over I Ri with respect to G cross with MIAI with respect to G. If you recollect the discussion we had for this in the planar case, this was always in the negative direction of Rij, this term. So you can already see that cross product of Rij with something that is collinear with Rij would be 0. So the cross product due to this term in the planar case is obviously 0. Now in the more general case, how does it still work out to be 0? That is something for you guys to think about. That is a little bit of homework for you. But you can see that the term, the cross product due to this term ends up being 0. So what you are left with is Rij cross with only Mi times this term. So you get sum over I, Rij cross with Mi alpha cross with Rij. Now obviously there is some abuse in this derivation, because when we are dealing with a rigid body, there are no longer a finite set of particles. This should really be an integral over dm, but I am showing a summation just to give you a sense of how that derivation works out. The other thing you can see right away here is that there is an alpha, but there is also an mr squared. All of these are I, right? And a summation mr squared is really where you get your moment of inertia. So this ends up being I alpha. And since all of these positions are relative to the center of gravity, this is really an moment of inertia relative to your center of gravity. So you get an Ig alpha. So if we go back to our right hand side equation, this simply becomes Ig alpha, but this is only valid when we have the rigid body assumption. When we are talking about a system of particles, you cannot write it this way. So let's clean this up. And after cleaning up, we have sum of moments of all external forces about O is equal to Rg cross MAG plus Ig alpha. So your sum of moments is equal to I alpha really follows from this equation. Further, when in static equilibrium we do sum of moments equals 0, again that is a special case of this. But remember, this is about center of gravity, and this term is also not to be missed. So this is an important equation, but let me also remind you of two other equations that we had seen before. One is the sum of all external forces acting on a rigid body is equal to the total mass times acceleration of the center of gravity of the rigid body. In this equation, if I take cross product with Rg on both sides, I would simply get Rg cross with sum of forces is equal to Rg cross MAG. And parallelly, let us break down this equation into two terms. If you remember, this is nothing but, Ri cross Fi sum over I. And I can write this as sum over I Rg plus Rig cross with Fi, and that I can write as Rg cross with sum over I Fi plus sum over I Rig cross with Fi. Now let us recognize that these two are exactly the same, So on the left hand side I have this, left hand side of this equation. I have this, and on the right hand side I have this. So I can cancel out that part of this moment with this, and what I have left I can then write as sum of moments relative to the center of gravity of all the forces is equal to Ig times alpha, where this moment of inertia is with respect to the center. Okay, now let's write all of these together. Let's clean up all of this, and we get sum of moments about center of gravity is equal to Ig times alpha. Now there is something important to note here. We didn't explicitly state it, but the assumption we were making here is that O is not an accelerating point. I should have mentioned it in the beginning. However, this equation is valid even if the center of gravity is accelerating, because it just follows from the equations. So these are two simple equations. My suggestion is only remember these. Don't try to remember all the special situations, parallel axis theorem, rotation about some other point. All of those follow from these equations. So it's always better to go back to basics when you're confused and apply the simplest form of these equations. Now let's move on. Now let's go to angular impulse and angular momentum. For that, let's go back to our basic equation again. This is Newton's law applied to a single particle. Now let us again do Ri cross both sides. But in addition, let us also then integrate with respect to dt on both sides, and sum over I particles. And when you do that, on the left hand side you simply get the angular impulse between time instant 1 and time instant 2. Now that is really, the integral is from t1 to t2. Remember, we are talking about time integral now. And the right hand side is really sum over I integral of Ri cross with MIAI multiplied by dt t1 to t2. So let's look at this term more closely. We can again write this as sum of two accelerations, Ri cross with Mi, acceleration of center of gravity, which I will now write as dVg by dt, plus acceleration relative to the center of gravity, which I will write Vi with respect to g dt multiplied by dt. And this one more bracket I'm seeing. Now this is very simple. Obviously the dt's cancel out. So you get one term which is Ri cross with Mi dVg, and your integral makes it just Vg. And you can bring Mi here with the summation. The first term really becomes mRg cross with Vg. And again I can move this m to the second part of this cross product, and the first term really becomes Rg cross mVg. So the second term is sum over I Ri cross with m Vig. Now here let's do two things. Let's assume we are dealing with a rigid body, and in case of rigid body, the distance between I and g is fixed. So this velocity simply becomes omega cross Ri with respect to g, and this Ri we can further write as Rg plus Ri with respect to g. Now if I do all of that, this entire term becomes Rg cross with mvg plus sum over I Rg cross with mivig plus sum over I Ri with respect to g cross with mi omega cross with Ri with respect to g. And then it should be obvious that Rg, since it's not dependent on I, you can take the summation in here, and sum over I mi vi with respect to g is 0 because you are measuring everything relative to the center of gravity. So only thing that remains is this term and the first term here. And this term again you can see, remember in rigid body it's really an integral. So integral dm r squared, that is again starting to look like a moment of inertia. So it's a moment of inertia times omega. So the right hand side of that equation ends up being Rg cross mvg plus Ig omega. And everything is measured relative to the center of gravity, therefore it is Ig. So let's put this back in that original equation, and what we get is angular impulse in going from time instant 1 to 2 due to all external forces is equal to Rg cross mvg plus Ig omega. And although we didn't discuss this, in this angular impulse, all the terms due to the internal forces cancel out, and so you are only dealing with angular impulse due to all the external forces. That is equal to Rg cross total mass times velocity of center of gravity plus moment of inertia about the center of gravity times omega. We'll make two more observations here. Just like last time, we can again think of moments about center of gravity alone. So angular impulse about the center of gravity in going from time instant 1 to time instant 2, we would get, just like last time, just Ig times omega, and this is applicable even if the center of gravity is accelerating. Whereas for this we have the assumption that we are taking moments about point O, which is not an accelerating point. Now the other thing we can do right here is, this is nothing but the total angular momentum of the rigid body about point O. Remember, this is valid only for rigid bodies. And if angular impulse is nothing but an integral dt, we can write this same equation in a different form where integral dt is equal to h. Then we can write it in the form that the total sum of moments about O is equal to HO dot. So the sum of moments is equal to the rate of change of angular momentum, and this also we can do about center of gravity. So in summary, what we have seen are really only these set of expressions: angular impulse, angular momentum, and you can write it in a different form, and sum of moments is equal to I alpha. Of course, there is one detail we haven't discussed, which is really the nature of the moment of inertia itself. It is not a scalar, but it's really a tensor. And I'd like to think of it as a matrix. It's most convenient to think of it as a 3 by 3 matrix. We will talk about it in a separate refresher capsule. Now, one of the questions I would ask you guys, in case you have watched the Martian movie, there is a discussion about a slingshot. They come up with a way to redirect the spacecraft and send it back to Mars in a relatively short period of time. Now I want you guys to think about whether it is related to angular impulse, angular momentum, whether it's related to linear impulse momentum, or is it a combination of those concepts and some other concepts. But an interesting fact there is, I don't know if you are familiar, but ISRO's Mangalyaan mission used that slingshot concept extensively. If I remember correctly, there were about 6 or 7 slingshots around the Earth before it was even launched towards Mars. So something you can look up. Okay, coming back, there are a number of other interesting things that come out of angular momentum. The gyroscopic effect that most of you are already familiar with, again comes out of this simple equation right here, and you can see it as just sum of moments is equal to rate of change of angular momentum. The other interesting thing is Euler's equations of rotation again come out of just this equation, and we will talk about that again in a different capsule. But that also leads to many interesting insights about rotating bodies and stability of spins, and that's again an interesting topic to discuss. So with that, let's close this session. The gyan of the day is really mix it up. And what I mean by mix it up is, oftentimes I find students, you would study one concept, then solve problems related to that concept. But then when you're faced with a totally different question about how can you explain the slingshot, it is very hard for most of us to connect which concept to use. So I think what is important while you're studying this is you study a little bit of angular momentum, then you solve a problem related to F equals ma, then you study a little bit of, so there's a lot of cross-linking that needs to happen in your mind for you to be able to have a bigger picture view of these concepts, rather than very niche view about these concepts. And I encourage the same on a personal level, even on other fronts. So while you're studying dynamics, play a little bit of badminton, listen to a little bit of music, and there is a lot of cross-linking that happens. Of course, you don't see it immediately, but after 10 years, 20 years, all of those have an effect. And to close off, remember, you can always learn anything you want. All the resources are available, in most cases, online. All you need is a little bit of commitment and patience. Even if you don't have much resources, you can always learn on your own.